We continue with Model 2, workbook open Model 2, sample project underscore B. We start with the workbook sample project tunnel. We have completed the WBS. All the groups now have cost elements in there, such as the NADM tunnel, TBM tunnel, access shaft. We also have our property cost, investigation, and so on. We have also, in the meantime, completed the schedule with a base schedule and a base schedule plus uncertainties. What we are still lacking are risks. So we now go to the workbook risk register, where we have prepared a folder for identified risks and one for unknown risks, and right-click on identified risks, press new cost element, and this time we do not select B, but we select IR, identified risks. We want to have one cost position and one time position, and press OK. We add a name to it. This is our R01 sample risk, which has, if it eventuates, a cost impact of 100,000 up to 400,000, most likely value 200,000, and a time impact of 40 days, and we will add a range to that by pressing Control and P. And we now can say the lower bound is 50% below the most likely value, and the upper bound is, for example, 75 above the most likely value. Press Enter, and now we have created our ranges in a different way, 20 to 70 days. We press Simulate and look at the results. What we see is that the P50 value, 212,000 for the cost, is little higher than the deterministic value of 200,000. That is because the distribution has a skewness to the right. 400,000 is further away from 200,000 than 100,000 is. So this is the reason why the P50 value is higher. And the same is true for the time estimate. Now let's add a probability of occurrence to that. Let's say the probability of occurrence is 70%, which means there's a 30% chance of nothing happening, and there's a 70% chance of the risk eventuating. Now this changes the look of the distribution function completely. The distribution density looks the same because the 0 percentile is not shown here, but you see the distribution function here has changed, and it has changed on the right side because now the first non-zero value is P30. In 30% of the cases, the risk will be 0. If I change the probability of occurrence to 30, the whole picture changes. In 70% of the cases, it's 0. And in 30% of the cases, the range that we have entered, 100,000 up to 400,000, will be the risk impact. If you compare this impact with the deterministic number, you see that the deterministic number is not a very good predictor of what's actually happening in this risk scenario. Because either it's 0 or it starts at, in the best case, 100,000. There's no case where it can be 60,000. For people who are not so familiar with RIAAT, we also have the software PRAT, which is based on Microsoft Excel. And we can enter risk fact sheets in PRAT. It looks like this. We have a risk identification section, risk response, qualitative analysis, and then the quantitative analysis, where we say what's the probability of occurrence or what's the number of events that we estimate, and then we describe a best case, most likely case, worst case, and put numbers to it. And we can take these risk fact sheets, and I will close it again, and import it into RIAAT by clicking Workbook, Import from PRAT, select a PRAT file that you want to import, select the folder where you want to put it, and then you have this interface where you can say import, and you will have your risk ready here. Simulate, And this is the same result that we get in the Excel file Pratt. You can see there's an indication that this risk was actually imported from Pratt. There's one more thing I would like to show you, and that is connecting our risk register to the schedule. I will go to the Gantt diagram, select base schedule plus uncertainties, take our sample risk, and drag and drop it onto, let's say, for example, NATM South first tube. Say it's an owner risk, and you see there's a small orange extension now, which indicates that there's a risk connected to this scheduled task. If I make this risk higher, so let's say I increase the probability of occurrence to 80% and I increase the mean impact to 60 days, for example, simulate again and go back to the schedule, we see that this extension has grown, and the visualization of this extension is always the deterministic value. So if the deterministic value changes, we see that the bar of the task has increased. To complete our risk register, we also need to take into account unknown risks. We do that by going back into our Excel file Pratt, and we have a risk fact sheet project prepared where we enter some basic information, enter the project phase, and then answer questions with respect to project maturity, project complexity, ground conditions or ground risk, market risk, and also a reduction of single risks. So if we have a very detailed assessment of single risks, which we assume in this case, we will reduce the benchmark value for the unknown risk, in this case by 65%. And then we come up with a result, which is 5 to 8 to 12%, range 5 to 12%, most likely value 8% as a markup on base cost. And this result is now implemented into RIAAT. We create a new cost element, cost component U, unknown risk. Let's call this unknown construction contract. And we select as quantity a percentage, 5, 8, 12. And as a unit price, or as the price, we now connect the base cost of the construction contract to our cost element. So sample project, tunnel project, construction contract. Base cost, and now there's a reference. If we change the base cost, this number will change also. 5 to 8 to 12% of our base cost from the construction contract. We simulate, and that's the result. Now we copy this one, and we make a second unknown for the indirect cost. We disconnect and connect again. Now go to owner's indirect cost, establish the connection, simulate, and now we have the unknown covered for the whole project. We have all the tools at hand now to build a basic risk register consisting of unknown risks and identified risks. And now's the time to look into a little more complex modeling into the capabilities of RIAAT and model an event tree. Let's assume the following scenario. We have a tunnel boring machine digging through the rock mass and reaching a fault zone. So the TBM is advancing through a fault zone. If everything goes fine, nothing happens. Then we are down there. But maybe the TBM advance is being halted. Then the risk eventuated. So the personnel on site will try to overcome this, change a few parameters on TBM operation, and maybe overcome this in, let's say, 1 or 2 days. Then nothing further happens. Or they're not able to overcome this. the rock mass squeezes onto the TBM shield and the TBM gets stuck and we have a deadlock. Now we have to take severe measures to overcome this deadlock, which will take weeks and months of work. And if we are lucky, these are enough and we get the TBM going again. Then we are down there, no further event. But there's also quite a chance that this is not enough and that we have to consider the worst case scenario, which would be a complete new tunnel, a TBM bypass tunnel, to unlock the TBM and to get it going again. This is the event tree that we want to model in RIAAT. So now let's go into RIAAT. Right-click on Identified Risk, New Cost Element, Identified Risk. We're only looking into time for this example. And we call it RO2 TBM Event Tree Analysis. We have three scenarios that we need to quantify. The first one is TBM advance halted. And the second one is TBM deadlocked. And the third one, our worst case scenario, is the TBM bypass tunnel. Now, before we look into the event tree, let's assess each of these scenarios. The TBM advance halted will take us about 1, maybe 2, and in the worst case, 7 days. If the TBM is deadlocked, it will take a lot more. It will take maybe at least 2 months, maybe 3 months, worst case even 4 months, until we decide it's not working, we have to build a bypass tunnel. And then on top of the measures we've already taken for the deadlock, we now build a bypass tunnel, which will take us at least, and that's the very best case, 100 days, more likely 180 days, and in the worst case, 230 days. These are our risk events, and we now want to model them in the event tree. We press this icon here, create new event tree. Click on this icon, edit event tree. And our event is TBM advancing through fault zone with 2 possible outcomes. First one, no further event. And the second one is actually we connect that TBM advance halted. That's our scenario. And if TBM advance is halted, either there's no further event or the TBM is deadlocked. And if that happens, there's either no further event or we need a bypass tunnel, which is the worst case scenario. Now we need to talk about probabilities of occurrence, and we assume in this project there's a 40% chance of the TBM advance being halted and a 60% chance of the TBM going through the fault zones without problems. After the TBM advance halted, there's a 20% chance of a deadlock. And after that, we assume that the measures we take to overcome the deadlock are enough in 50% of the cases, and in 50% of the cases, we will need a TBM bypass tunnel. So we have all the probabilities of occurrence lined up. We have all the events quantified, TBM advance halted, deadlocked, bypass tunnel. So our event tree is up and ready, and we can simulate it, update this cost element. Now let's close it and look at the results. So there's a very high chance of almost nothing happening. Then there's a small chance of the deadlock, and then there's a small chance of the TBM bypass tunnel. You can see that in the distribution density here. If you look on the right side at the distribution function, there's a 60% chance of nothing happening, then about 30% chance of very small things happening, and then there's about, let's say, 8% chances of very drastic measures needed to overcome this risk scenario. So this is a Classic, what we call low probability, high impact risk. I would like to show you one more thing now. For this event tree to take place, we have selected a probability of occurrence of 100%. If we say there's only a 50% chance of meeting a fault zone at all, we can change this to 50% and run the simulation again. If we say in this project we will meet 5 fault zones on average, we can change this percentage here to a Poisson distribution and say on average we will have 5 fault zones in this project. So the event tree is run 5 times in a row, which will of course change your distribution function. There's only about 15% chance of nothing happening, and then there's about 30% chance of severe measures taking place.